Now let's talk about the third category of rendering resources, shaders. When analyzing shader performance, we need to understand one fundamental question. What parts of memory does a shader actually affect? This is important because texture and mesh resources, which we discussed earlier, are relatively straightforward. Textures usually occupy memory under the graphics resource category. If read-write is enabled, additional CPU-accessible memory is allocated under native objects. There may also be a small managed memory footprint. So although textures have multiple memory components, their behavior is still relatively predictable. Shaders are different. Shader resources interact with memory in a much more complex way. There are three major areas to consider. First is the native object layer inside the engine. In newer Unity versions, shader memory is primarily tracked within the native runtime object system. You can observe this through the main profiler view. Inside the native object category, you will find the shader's core memory allocation. Second is the GPU program layer. When shaders are warmed up or participate in rendering, the system generates GPU program objects. This behavior is consistent across platforms. On Android, these allocations usually appear in native heap. On iOS, you can observe similar behavior inside the rendering thread allocations. Let me zoom out for a moment. Over the past few years, we've observed a shift in performance debugging. Many game performance issues are no longer solvable purely at the engine layer. Increasingly, we need to analyze system-level memory behavior. Besides engine memory, hardware-level factors such as thermal throttling and system allocator overhead can also influence performance. That's why we encourage developers to monitor not only engine memory metrics, but also system memory usage. One of the largest system-level memory contributors is native heap usage. For deeper analysis, tools such as Profeto-style system profiling utilities can be extremely helpful. These tools allow you to inspect which shared library files are responsible for specific allocations. In one of our test projects, native heap memory reached over 900 megabytes. This is extremely rare and represents a severe memory issue. In that case, nearly two-thirds of rendering thread memory was associated with a node called Vulkan GPU program. This memory is related to GPU program variants generated when shaders participate in rendering. Now let's look at the iOS perspective. Using the allocations profiler, we observed similar behavior. Under the rendering thread group, particularly under GFX Vulkan pipelines, there is a memory queue labeled Create GPU Program Queue. The name itself clearly indicates what is being allocated. This is one of the most commonly overlooked shader costs. In projects with large variant counts or extremely high rendering complexity, this component can become a major memory consumer. So what is the main driver of shader memory growth? The answer is simple: shader variant count. Increasing shader computational complexity is not usually the goal of memory optimization. That decision is tied to GPU performance and visual design. Instead, memory optimization focuses on variant management. Across many projects we studied, the number of shader variants used in production rendering was far smaller than the number of variants actually packaged or precompiled. This mismatch is the core problem. To explore this, we built a test. On Android, we constructed a shader containing 10,000 variants. Each variant computationally simple. Using shader variant collection, we divided variants into 10 groups, each containing about 1,000 variants. During runtime, we gradually warmed up these variants. Before and after variant warm-up, we measured memory usage. First, engine-level memory. Inside Unity profiling tools, we tracked two components: shader native object memory, untracked memory. Interestingly, shader base memory increased by about 30 megabytes, but after warm-up, some memory metrics actually decreased. This is a somewhat unusual phenomenon. Another important metric is untracked memory. Many projects struggle with this category, because engine profilers alone cannot reveal the full memory picture. When using system-level profiling tools, we observed something interesting. Native heap memory and graphics memory showed very similar growth patterns. This confirms that shader program generation directly affects system-level allocation. Overall process memory, what we call PSS total, also increased significantly. Earlier, I mentioned that warm-up can sometimes reduce shader-based memory. Here is why. During warm-up, shader GPU programs are generated early. Runtime shader compilation overhead is shifted to initialization time. Regarding the earlier point that pre-warming can reduce the runtime memory usage of the shader itself, we can look at a memory change curve captured by the GameOptim online memory profiling tool. Our tool identifies resources as the same if they share the same name, same memory usage, and some identical properties. The shader phenomenon is actually quite special as it breaks this mechanism. As a result, we found a bunch of shaders with the same name called unlit warm-up. When you check their memory usage, you'll see that their life cycle is continuous, but their memory footprint gradually decreases. Therefore, we counted them as 10 different resources, when in reality, they are the same resource. This is what we mean by pre-warming causing a reduction in the shader's own memory usage. That is, it's likely that at runtime, during the shader.create GPU program operation, the memory information of the shader itself is transformed into the memory footprint required at runtime. Now let's look at the overall memory change during the pre-warming process. Returning to the perspective from our system-level tool, pay attention to the graphics section. First, native heap. It was only about 20 megabytes, but after pre-warming it rose to over 250 megabytes. Then graphics itself. It was only about 62 megabytes, rising to 287 megabytes. This is the significant memory difference caused by shader pre-warming. After discussing the phenomenon, let's now look at the actual problems encountered in projects and their solutions. In practice, we find that in many projects, the root cause is that too many variants are included in the build. As a result, when loaded from the build into memory, the memory usage of the shader itself also becomes higher. We see many projects where a single shader can occupy tens of megabytes. The page you're seeing now is a report from our asset bundle analysis. In fact, after recent version updates, we can now obtain a lot of information about asset settings within the build, as well as other parameters. This includes the shader variant usage in the build. Here you can see that many shaders have variant counts in the thousands. This is clearly unreasonable or indicates a problem. It's easy to understand. In the vast majority of modern mobile projects, even for a highly versatile shader, for example, one used for models, characters, and effects simultaneously, simply using different feature toggles, the actual number of variants used in rendering is typically only in the tens or hundreds. If the number of variants entering the build, and ultimately memory, reaches thousands, that is clearly not expected. The most fundamental reason for this phenomenon is that there is room for optimization in how we control keywords and variants. In the process of variants participating in rendering and pre-warming, leading to high memory usage, the phenomenon we just mentioned, the time cost of the shader create program operation itself is also involved. If we don't collect variants, shader create GPU program is automatically triggered the first time a shader variant is used in rendering. At that point, memory is allocated incrementally. Our purpose in collecting and pre-warming variants is precisely to reduce stuttering. Some project teams might wonder, originally, memory wasn't an issue, but now after collecting variants and pre-warming them all at once at game startup, aren't we effectively loading and caching all that memory up front? Could this challenge our memory budget? However, we believe that when the overall process of variant collection and pre-warming is reasonable, in the ideal scenario where we collect, cache, and pre-warm only as many variants as are actually used in rendering. Under that premise, memory is controllable. Conversely, even without pre-warming, memory would still gradually rise to the necessary amount for rendering as variants are actually used. So the memory issue caused by shader pre-warming we're discussing does not fundamentally contradict our earlier recommendation to collect and pre-warm variants to reduce stuttering and CPU time. Returning to the point, the additional memory allocated at the system level on the native heap and GFX memory sides due to pre-warming, as mentioned earlier, is fundamentally controlled by ensuring our pre-warming does not exceed what is actually needed. For example, some projects might call an API like warm up all shaders for pre-warming, or their variant collection results are overly conservative. To avoid incomplete collection, they end up collecting far more variants than needed. In such cases, pre-warming will have a significant negative side effect. So the core principle is to not exceed what is necessary. At this point, we should revisit the topic of variant collection and stripping. Essentially, an excessive number of variants stems from having too many keywords. Keywords are mainly divided into two types: shader feature and multi-compile. Among these, shader feature is affected by the variant collection results. The Unity engine automatically strips a large portion of them. Variants not present in the collection results are not forced into the build. However, multi-compile is still used very frequently in most projects, and it causes variants to increase exponentially. To address this part of the memory usage, we cannot rely solely on variant collection results. Instead, we need to consider using the on-process shader callback to proactively disable keyword combinations that are certainly not needed during rendering, or even directly strip variants one by one based on the complete variant collection results. Of course, the maintenance cost of this approach is relatively high, but the performance benefits are also considerable, as we've discussed. From the perspective of variant collection, our blog also contains some related discussions, such as the process for complete variant collection. Many project teams are already using this process in practice. We also recommend that you consider other methods of variant collection, as the actual needs of different projects do vary. We understand that the UAsset plugin has its own built-in variant collection functionality, which we won't elaborate on here. We believe the variant collection evaluation of this tool is quite insightful, and you may want to pay attention to this feature. UAsset not only helps manage assets, but also provides variant collection functionality. After discussing the impact of shader variants, let's briefly mention an optimization tip beyond variants. We may have spent a lot of time reducing variant counts and optimizing shader memory usage, but there is a setting that is very easy to change, yet yields significant benefits. In the shader variant loading settings, the default values are 16 and 0. In our tests, we changed these values to 8 and 1. Some projects have even set them lower. Our testing so far has shown no clear negative side effects, but it does lead to a noticeable reduction in shader memory usage. For example, a PBR shader that originally used 32 MB of memory dropped to nearly 20 MB. The effect is quite significant.